Hey everyone, so today we are going to talk about one of the very important method in optimization problem. Okay, so the method is called as Lagrange multiplier method. Now this is the third lecture on this optimization problem. So earlier two links I will post in the description. So the first one was to find the maximum and minimum value of the function. That means to optimize the function. But there, when you had a function, for example, if you had f of xy is equal to x square plus y square minus 2xy. Suppose you want to maximize or minimize this function. Now here there was no restriction on x and y. Your x and y can be anything in R2. So when there are no restrictions, no constraints, then such kind of problems are called as unconstrained optimization problem. And to find the maxima or minima of this, we took the help of the Hessian matrix. This is one notation. Many times people write grad square of f. This is another notation. Then in the next lecture, we didn't have this scenario. We had a scenario when the domain is closed and bounded. Closed and bounded means what? You want to find the maximum or minimum value for this function, but your x and y should lie in, suppose, closed and bounded this triangle, or suppose closed and bounded this rectangle, or some circle, closed and bounded circle, or a rhombus. So whenever you have closed and bounded, then how to tackle those scenario that we saw in our exactly earlier lecture. Okay, and there we saw that we need to divide into cases, interior case and the boundary case. For interior case, we again take help of this. You take the partials equal to 0. And for boundary case, if you recall, in the earlier lecture, I took a temperature problem. I gave you a temperature function. And what was the domain? Domain was this disk. So for interior points, we took partials equal to 0. And for boundary, what did we do? So if I recall, I have not seen that function. But if I recall that function, I think the function was t of xy equal to x square plus 2y square minus x. Something like that. And what was the constraint? So this was the disk of radius whatever, say disk of radius 1. So for interiors, you take partials equal to 0. And for boundary, you have x square plus y square equal to 1 boundary. So what did we do? We just found y square and we substituted here y square. So you have x square plus 2 into 1 minus x square minus x. And then this was ultimately a function of one variable. And then you applied your single variable techniques, t dash of x equal to 0 and so on. But now the problem is this substitution method doesn't work always. Okay, I will take an example where you will see that this substitution doesn't always work. So what is the reliable method? Then comes this person. Okay, this person's method, that he gave you one reliable method to find the extreme values. Okay, now why the substitution doesn't work always? So there is one nice example. So suppose if you want to minimize a function. So if you have a function, say f of x, y, z is equal to x square plus y square plus z square. And I'm giving you a constraint that your xyz should lie on this x square minus z square minus 1 equal to 0. So this is the constraint. Well, this is nothing but a hyperbolic cylinder. Actually, let us try to see this using GeoGebra. So here you can see the GeoGebra. When you put x square minus z square minus 1, this is the surface you get. The blue axis is the z axis. You can see that the surface is not touching the z-axis. Your red line is the x-axis, green line is the y-axis. Okay, so the point will not lie on z-axis, and from here you can see actually this point 100 and minus 100 are the points closest to origin. Okay. So I hope this can visualize this hyperbolic cylinder. Now let's find this point. Now using GeoGebra, we have seen that it is, so if this is my z-axis, this is x-axis and y-axis, so this is my xy plane. So this is the hyperbolic cylinder, and you have seen that it is not cutting the z-axis. Okay, so if I try to draw some kind of rough figure, like if I just take the projection, this is the sheet, and it is not cutting the z-axis. And you can see that minus 1 0 0 and 1 0 0. The points on x-axis, they are closest to the origin. And that's what you want to do, right? So suppose here if you have a square root, so what this give you? This will give you a distance of a point xyz from origin. So actually I want to minimize this function, means what? I want to find a point on this cylinder whose distance from origin is minimum. And from diagram we can see that 1 0 0 and minus 1 0 0, these are the points whose distance from origin is minimum, and they are on our constraint. What is the constraint? Hyperbolic cylinder. Okay, so graphically I can see, so I could answer the question. Suppose if I don't know the answer, then what will you do? So the first thing is, what you do is you write your z square as x square minus 1, and now you substitute the value of z square in that. So you have f of x y, your function will now only be in terms of x and y. And let me remove the square root, because if I keep the square root, then while taking the derivative you have 1 upon 2 root, because derivative of square root is 1 upon 2 square root. So I will ignore the square root. This ignoring is possible. Why? Because if you get a point a comma b comma c, you find f of abc, which is a square plus b square plus c square, and then take the square root. Then that is the minimum distance. Okay, so for simplicity of the calculation, we never take square root into the picture. Okay, now what is f of xy? It will be x square plus y square plus z square is what? X square minus 1. So this is what you get. Now what you do? Now this is a two variable case. What you do? You take partials, equate it to 0. So what do you get? You get 4x equal to 0, 2y equal to 0. So you get x equal to 0, y equal to 0. But that means they are saying that that point is lying on z-axis, because only on z-axis your x and y both components are 0. But we know that your hyperbolic cylinder is not touching the z-axis. Okay. So, or otherwise you can put the value here. You put value of x and y in here. Your x is 0. So you have z square equal to minus 1, which is not possible in real case. Okay. So if you are solving by substitution, we are getting that x and y has to be 0. And if x and y is 0, when I put here, I get z square equal to minus 1, which is not possible. So this substitution method says that no such point exists. No such point exists. But which is wrong, right? We have already seen that 1 0 0 and minus 1 0 0 are the points which are closest to the origin, and they are on the cylinder, hyperbolic cylinder. So that's why the substitution method doesn't always work. Okay. Now here, actually if you go by other way, other substitution, now here you can say actually you can do two substitution. First we did was z square equal to, now suppose if I do x square equal to z square plus 1, then if I substitute this over here, I will have a function in y and z. So what I have is y square plus 2z square plus 1. Now again you take the partials, equate it to 0, f with respect to y, f with respect to z, you get y and z 0, and if I put z equal to 0 here, I get x equal to plus minus 1. Therefore I get 1 0 0 and minus 1 0 0. So these are the 2 points, and if you find this value, you get 1. So with this substitution you get the answer. But like again, like when you have a constraint which you have a problem with say 10 variables, 100 variables, so obviously it's not possible to see which substitution will be correct. Okay, and also you cannot visualize the graph. Therefore substitution is not a good method to solve such kind of problems, and that's why you need Lagrange multiplier method. So let us try to see the statement, and then let us take some examples. So here is the method. So method says if you have f and g which are differentiable functions, that means what? Their partial exist and they are continuous in simple language. Okay, and your gradient is non-zero. Now what will be the gradient? It will be it's a vector consisting of partial derivatives. So grad g is g with respect to x, comma g with respect to y, comma g with respect to z, and at least one should be non-zero, all should not be 0. Okay, so it's a vector is a non-zero vector where this is a surface, like earlier case that hyperbolic cylinder was the surface, x square minus z square minus 1. That was my g. Okay. Now to find the local maximum and local minimum values of f, what you do is you solve these two equations. You find first grad f equal to lambda grad g. From here you will get some equations and use that in the second one, the constraint, to find the value of x, y, z lambda. So simply keep these two things in mind and you find the values of x, y, z lambda. Now here I have stated the theorem for a 3 variable case. The same thing works with 2 variable, 4 variable, 5 variable, 6 variable and nth variable in general. Okay. If you have a 2 variables x and y, in that case your gradient will be 2 components, f with respect to x and f with respect to y, g with respect to x and g with respect to y. When you have 3 variables, then it will have 3 components, 4 variable, then 4 components. Okay. So let us take one example so that it will be clear on how to use this method. Okay, so let us solve this problem. You have to find the point on this plane which is closest to this point. So now here function is not given to you directly, it is given indirectly. So what is the function? So if x, y, z is a point on a plane, what will be its distance from 1, 1, 1? So Euclidean distance formula. So I call f of x, y, z equal to square root of x minus 1 the whole square plus y minus 1 the whole square plus z minus 1 the whole square. Now again for simplicity, let me not take square root. Now I want to minimize this function. Suppose if they say origin, then it will be x square plus y square plus z square. So depending upon the point, your function will change. Now I want to minimize this function. What is the constraint? Your g of x, y, z. What is the constraint? The constraint is it should lie on the plane. So x plus 2y plus 3z minus 13. So these are the two functions I want. Are they differentiable? Yes, because you can take the partial derivative. They will again be polynomials. They are continuous. Good. Is the gradient non-zero? Yes, it's a non-zero vector. So what is, you solve that equation. So what is the first equation? Grad f. F with respect to x, comma f with respect to y, comma f with respect to z is equal to lambda into g with respect to x, g with respect to y and g with respect to z. Now you equate, you get 2 times x minus 1 equal to lambda, then 2 will get cancelled, 1 minus 1 equal to lambda and 2 times z minus 1 equal to 3 lambda. Okay. Now from this, what we usually do is we find the value of xyz in terms of lambda, and we know that xyz is satisfying this equation. Why? Because it is on the plane. So usually we find xyz in terms of lambda, we plug in over here, you find the value of lambda. Once you get the value of lambda, you plug in over here, you get the value of xyz. Usually that's the trend and it usually works out. Okay, so otherwise you need to do many calculations sometimes, but it's okay. Most of the times this will work. So what is your x from here? You can see that your x is nothing but 1 plus lambda by 2. What is your y? 1 plus lambda. What is your z? 3 by 2 lambda plus 1. And we know that your xyz has to lie on this plane, on the surface. So g of xyz equal to 0 will imply 1 plus lambda by 2 plus 2 plus 2 lambda plus 9 by 2 lambda plus 3 minus 13 equal to 0. So I substituted the value of xyz over here. Now you get the value of lambda, right? So now I don't think there is much to solve, or I don't think you will get stuck now. What is this? You have 9 plus 1 10, so 5 plus 2 7 lambda, 2 plus 1 3, 3 plus 3 6 and 6 minus 3 is minus 7. So your lambda is 1. So what will be your xyz? Your xyz will be 3 by 2, 2 and 5 by 2. You can see that this point lies on the plane, and when you take f of xyz, means 3 by 2 minus 1 whole square plus 2 minus 1 whole square plus 5 by 2 minus 1 whole square, and you take the square root, that distance is the minimum distance. Okay, so this is how you can solve such kind of problems. So I hope this is clear. Now let me give you two homework problems on this, and then we will see how to tackle the case when you have two constraints. So in the first one, you have to find the maximum and minimum values of this function, but the condition is your x, y, z should lie on the sphere. So this is your f. What is your g? X square plus y square plus z square minus 30. So that's your g, and apply the method, find the points and find the maximum and minimum value of f. Second one, find the points on the surface this. So what is your g? xy minus z plus 1 or z minus xy minus 1. So that is the g nearest to the origin. So what will be your f? It will be x square plus y square plus z square. Okay, don't take square root at the start because otherwise the calculation will be complicated. Simply take x square plus y square plus z square and solve that, and this g, find your x, y, z, and finally when you get the point, say ABC, you find f of ABC, which will be a square plus b square plus c square, and at the end do not forget to take the square root, because in the distance you have to take the square root. Usually people find ABC, they find f of ABC, which is a square plus b square plus c square, and they write, then they say this is the minimum value. No, you have to take square root. Okay, so this is how you tackle the problem with one constraint. Now how to tackle the problem when you have 2 or 3 or 4 constraints? See, you can have many constraints, like if I want to give an example, suppose you have a courier company, like this FedEx or DHL, these are the big courier companies. When they want to do the transportation of the parcels, what is the main aim? They want to minimize the cost. So what is the function? Whatever the function you have, like you have to minimize the cost function. Obviously, then only you can earn the profit. But then the constraint, what are the constraint? Like suppose you want to give thousands of parcels. The constraint is you have to go to this route, that route, that route. That is one constraint. You have to make sure you want to give the salaries to the employees. So you have to make sure you earn that much of the amount. So that is the another constraint. One more constraint is the weather. You don't know how the weather will be while transporting. So that might add a cost to your profit. Okay, so that is another constraint. Fuel is one constraint. Like there are many things one has to consider. So for one problem, you can have plenty of constraints. That's when you go to the real life, when you do modeling, that time you will realize the importance. But maybe the example which I give just now, that might not be a good example. But yeah, transportation problems are one of the very problem of interest in the real world, right? Because everything is transport and everybody wants to minimize the cost and maximize the profit. Okay, so that's why one should know those things. Okay, actually there are plenty of things to say, but okay, let's not get distracted. So this is we did for one constraint. Now let us try to solve the problem for two constraints. So now here I want to maximize this function subject to these two constraints. So what does the Lagrange multiplier method says? If you have f, let me call g1 and g2. Okay, so f is this x, y, z. What is your g function? Say g1. g1 of x, y, z is x plus y plus z minus 40. And g2 of x, y, z is nothing but x plus y minus z. You can write, it's good to write f of x, y, z. Let's say it's obvious, I'm writing f is this, that means f has to be of 3 variables. But it's good to write f of x, y, z equal to this, g1 of x, y, z equal to this, g2 of x, y, z equal to this. So when you have such thing, your f, g1, g2 should be differentiable. Your grad of g1 and grad of g2 should not be parallel, one needs while proving. In such a scenario, you simply solve grad f equal to lambda grad g1. When you had one constraint, you only had this thing. Now when you have two constraints, you will have two things over here, two constants, lambda and mu. So this is for one equation. Another is the surface, g1 of xyz equal to 0 and g2 of xyz equal to 0. So you take help of these three equations to find the value of lambda and mu. So from this you will get some equations involving lambda and mu. Then you take the help of these two equations to find the value of lambda and mu. Once you get lambda and mu, you can come back here and get the value of x, y, z. The same idea which we had earlier. When you have three constraints g1, g2, g3, then lambda grad g1 plus mu grad g2 plus some say delta grad g3, g1 equal to 0, g2 equal to 0, g3 equal to 0. And that's how the system works. Okay, now using this, let us try to solve this problem. Okay, so you have f g1, g2, so I am erasing this as if now. So what is grad of f? It is yz, f with respect to y and f with respect to z is equal to lambda times g with respect to x, y, z plus mu times g2 with respect to x with respect to y with respect to z, because g2 is x plus y minus z. So what the first thing you have yz equal to lambda plus mu, you have xz equal to lambda plus mu, and you have xy equal to lambda minus mu. And what are the two things you have? You have your g1 and g2. Okay, so I don't need this as if now. So what is your g1? g1 of xyz is nothing but x plus y plus z minus 40, and your g2 of xyz is x plus y minus z. This is your g1 and g2. Okay, now from here you can see, now here you don't have lambda and mu directly, so you have to play with the equations. This is just the playing with the equations. So from these two you have yz equal to xz. Now don't cancel z, okay, that's a very bad habit. So y minus x into z equal to 0. So either z is 0 or y equal to x. Okay, that's one thing. So if your z is 0 and y equal to x, now is z equal to 0 possible? No. Why? Because if you observe, what will be, it will satisfy this equation. So when I put z equal to 0, x plus y is equal to 40, and you here g of x comma y comma 0 equal to 0, right? g2 equal to 0. So this equal to 0 means your x plus y equal to 0. My z is 0. We are seeing that whether z equal to 0 is possible or not. From here you can see, can you give me x and y such that their addition is 0 and addition is 40 as well? No. Or you just subtract, you get 40 equal to 0, which is not possible. So therefore z equal to 0 case is not possible. Okay, so only case is possible is y equal to x. So when you do y equal to x, what do you get? X plus z equal to 40, and here you have x plus x minus z equal to 0. So you have 2x plus z equals 40, and I have 2x minus z equal to 0. If I simply add them, 4x equal to 40, so x equal to 10. Once your x is 10, what is your y? Your y is also 10. So your x is 10, your y is also 10. Now you want to find your z. How will you find z? Anywhere. Either you plug x equal to, it should satisfy both the equation, right? So what do you get? You get, from here you get z should be 10 and 10 20. So z should be 20, and this will imply your z should be 10 plus 10 is 20, and 20 minus 40 is minus 20, again z equal to 20. So what point do you get? The point you get is 10, 10, 20. So no need to find lambda and mu in this case. So sometimes you may need to find lambda and mu, but sometimes you will have some good equations. Just equate and try to see what conditions you are getting, and simply use g1 and g2 again and again and see whether which of the cases are possible and which are not possible. So that's usually an idea. There is no standard algorithm. You have to just play with the equations to get the answer. Now let me give you a homework problem for practice. So here is another problem. You need to maximize. So this is your f. Your g1 is x plus 2y plus 3z minus 6. Your g2 is x plus 3y plus 4z minus 9. Again use the method and try to find the value x, y, z which will maximize the function. So these are the three homework problems for you, and at the start also we did one example by substitution, like x square is equal to I think z square plus 1, and that gave us the answer plus minus 1 comma 0 comma 0. Do that problem as well using Lagrange multiplier for the practice. So I hope this is clear. If you have any problem in which you are having doubt, you can ask me in the comment section, or if you have any other doubt in this, like there can be some. For example, in the earlier example, we only got 1 point, 10, 10, 20. Now what is the guarantee that when I put that point in the function, it will give me the maximum value? So this could be a one question. If you know the answer, you can comment. If not, then you can ask me. But yeah, I will wait for the answers. So I hope everything is clear, and if yes, then do not forget to like, share and subscribe. Thank you.